And we come to our next speaker, Mark Geitz from T-Labs, Deutsche Telekom. You can already see it from the nice color here. Mark has himself been working excessively on the introduction of quantum technology into, like say, the test part of the Deutsche Telekom network, I would say. You also had some very nice demos, which I think go way beyond just your network. Now we will hear his talk about quantum security at Deutsche Telekom. Welcome, Mark. Stage is yours.
Yeah, thank you. Do you hear me?
Yes.
Yeah. Okay, that's all. It's not mute. Yeah. Okay. So, thanks for the introduction. I'm from a telco operator. Yeah. So I'm from a dissemination partner, so to say, to all what's been done here. I am working for T-Labs. That's a small organization located in Berlin. Winterfeldstraße is one of the oldest telecom buildings in the city, also prior to World War II, with manual switching and all that has been installed there. And you see my team, it's actually double the people, it's not all of them in my team. And the goal is to investigate quantum technology. I mean, we started out with QKD, went into PQC, PLS, and all that kind of stuff. And we're a demonstration engine. Yeah. So in the role of the company, I mean, we take in the new technology that's in the labs of the universities, try to get it out, implement it in the scope of a telco operator. Yeah. And see what's in. Yeah. What we have to do. Are we ready? Our network's ready for the technology? Yes or no? That's, by the way, I don't have a picture later. That's our QKD installation there that you see with the screens. Yeah, so we have it running since 2021. Yeah, it's continuously running, very stable, and it's operating in the Berlin network. What's our research focus? Yeah, today, I mean, that's why it's red. One of the key research areas was how can we secure our networks, provider networks in the future? Yeah, and there are lots of technologies on the table. Yeah, PQC, QKD, PLS, what have you. That's also the scope of this talk. Yeah, how we actually get this together in a way that it makes sense. But we're also doing more. We're part of the QRX project for quantum repeaters. Yeah, so we want to use our network to build a test instance of the quantum internet. Yeah, so generate, distribute, eventually sometimes store, detect entanglement, expose it to users, run easy quantum communication protocols. I think we are pretty much set for that. We have good partners and in the projects, and we are doing progress. I have some slides at the very end. And I mean, there's also always the question, I mean, what is the role of quantum technology for future networks? And there is quantum inspired, quantum classical, network-centric, optical quantum computing, maybe. I don't know. So we're not so far in that respect, but that's on the roadmap. But I start completely differently. Yeah, so I start with PQC, and I really wonder that at 11:45, nobody has ever mentioned one of the standardized PQC algorithms. Just here you have them in full beauty. They're called FIPS 203, 4, 5. There's key encapsulation for encryption. There's signature for authentication, and there is hashing. Yeah, they're called Kyber, dilithium. They're all built on a common library, and Sphinx for hashing. That's the beauty. And this is something, I bring this here so explicitly, that's something we cannot ignore. Yeah, I mean, the world somehow has decided, yeah, on a new generation of cryptography, yeah, asynchronous cryptography. And I don't want to repeat. I mean, Caroline, you showed all the advantages that are around. I mean, it serves for everything, if you like, except for this future-proof, everlasting security. So I mentioned it in a way here. There's no security proof. That's the only downside that we see. Yeah, for the rest, it's pretty cool. Yeah, and you can apply it. It's open source. Everybody can use it. Yeah, and what will happen now, in principle, it's standardized. Yeah, the cryptographic community will now re-implement, I would say, to get rid of side channels. Yeah, when it's re-implemented, maybe certified, it's going to be part of every operating system. Vendors will adopt it. It will come to the world. Everybody can use it. it's going to be there. Yeah, in 5 years from now, everybody has PQC. This is what the world thinks about PQC. Yeah, it fits better here in this context. I just sum it up. Yeah, what do the security agencies say? So security agencies are BSI, NIST, ANSI, British Cybersecurity Service, and all others more. I mean, there's a common opinion. Yeah, they all say, guys, industry, go to PQC. Yeah, endorse PQC. There are additional recommendations. Do it together with classical cryptography, yeah, to be, let's say, downward compatible, if you like. But do PQC. QKD, for instance, do for niche applications. Yeah, we don't say we're not against it, but it's not ready. They say, yeah, be careful. Yeah. The governments. I mean, there's a very strong opinion from the United States. Yeah, there are these national security memorandums, and there's even a public law. Yeah, that forces now United States government to endorse PQC, to implement it. Yeah, this means for every corporation that does business with the United States, they will also have to do PQC, obviously. Yeah, so that's why it's going to be in all the communication systems. For the EU, there's a recommendation to go for a migration roadmap, and in Germany, I mean, there's an action plan, yeah, to also come up with a migration plan on how to get to PQC. If you look at the standardization bodies, NIST publishes standards, ETSI is on top of it. Yeah, they have work groups, 3GPP, yeah, and GSMA. They have task forces. So there's really work going on, yeah, how to get, let's say, PQC into communication systems. On the telco peers, Vodafone, pretty big. They invested quite a lot. I mean, we didn't, unfortunately, we did also, but not that much, not in that level. But Vodafone is actually part of the PQC task force of the GSMA. There is some other players in there like Vodafone, Orange, Telefonica, and SKT. There's the Korean telco operator that is also very noticeably active. Yeah, so they have this QKD ring in their country commercially. Yeah, but they also now go into PQC because they see PQC is a way, let's say, to get international connectivity in a quantum safe way. Yeah? At the end of the day, in the summary, there's a big trust thing. Yeah, I mean, the only downside of PQC is they cannot prove it's good for all eternity. Yeah, that's why we have to trust. It's very important. Yeah, it's trust. And we trust the last 30 to 40 years. Yeah, with RSA, with ICC, we always trust. We believe the cryptographers did their job. We have to monitor. Yeah, but it's a trust thing. But the belief is, yeah, in the next 5 years, people will learn to trust as they trust the current cryptographic systems. Yeah, and I would say, my personal opinion, 99.9% of the communication is okay with that trust. I mean, when we write emails, Janis, I mean, I would say PQC encryption would be fine. Maybe not for the secret services, yeah, for the military applications, for the governmental intertalk. Yeah, they're maybe different. Yeah, so these are their niches where you want to do more. But at the end of the day, when somebody asks me for a recommendation, I always say the following. Recommendation 1, do PQC. Nothing more, do PQC. All networks, all applications, everything. It's going to be there anyway. Do it. Next, second one is, if you don't trust, if you're not a believer, that this is enough, you have to do more. Yeah. Then you have to come up with a second key exchange, or you have to exchange a second security factor. Yeah. And which is a random number. And most of the cryptographic protocols like VPN, TLS, IPsec, they all have this WireGuard. Yeah, they all have this interface for a pre-shared key. Yeah, and it's meant in a way that when you do your session key exchange, you have this pre-shared key and inject it, you combine it, and you have something better for a cryptographic key. Yeah, but now we have all these neat key exchange mechanisms, right? So we can use them to exchange a key, inject it, and have a better key. And then in principle, the final encryption key is then built on different security artifacts. Yeah, might be useful for special customers, but it's expensive. Yeah, you have to do more. Step 3 is actually the combination, yeah, of the two keys. That's my main message of the talk. I'm very clear on that. Yeah, so this is really my honest belief. Yeah, this strategy to go forward really makes sense. Yeah. Now, what can you do for this second factor? Now it comes. That's my favorite. Yeah, you scale. This means you use KM, SIG, PQC, yeah, to not just exchange one random number, but you do it with 5, 10, I don't know, n random numbers. And you combine them at the endpoints, and you secure the transmission by different PQC, SIG, and KEM algorithms. Yeah, the attacker would have to get hold of all your networks, which is rather impossible. He would have to break all the PQC algorithms, which is very, very impossible. Yeah, and at the end, through the combination, you get a very strong encryption key. On top of that, that's all implemented. Yeah, so we connected actually the QKD networks in Madrid, Berlin, and Poznan with such a scheme, and it worked. Yeah, you could forward a key from a QKD node in Madrid to a QKD node in Berlin. Yeah, through a multipath PQC channel. On top of that, we did even more for a Korean project. We put Shamir secret sharing on that. Yeah, so we have multiple paths. So you code the random number that you want to ship into, let's say, a redundant coding, Shamir, yeah, where you send 5 messages, and if the receiver gets 3, you can reconstruct the random number. Yeah, that's even also information theoretically secure. Yeah, if your random number generator is good enough. It's going to be live, I would say, end of year with SKT. You could also do QKD. Here it comes. That's my only quantum slide in the first part. Yeah, I don't have to explain it, right? You do QKD key exchange in this in this case with a entangled photon source. You do a measurement, and you get your encryption keys. It's a different technology. Yeah, it's a physical layer security technology that is giving you maybe some more benefits than the first one. Yeah, because that's the only complexity driven. I think you can also do wiretap codes on a mobile network. We did lots of computations here with a team of Holger, where we looked at different embodiments, and we found embodiments where we believe this method is also capable to securely transmit encryption keys. It also can transmit the entire message, yeah. But in principle, it can also encrypt the encryption keys and deliver encryption keys securely. This also fits perfectly with PQC, right? For me, this is a very cool solution, yeah, to combine PQC and that for mobile networks. Now you have two technologies that are, let's say, contrary to each other. Yeah, one is actually securing against attackers with big computers. The other one is securing against attackers with big antennas. Yeah, and that's why I like it. And there's even a fourth one we implemented, which is actually a random number beacon. Yeah, just like the NIST random number beacon, you get the beacon, you have a pre-shared secret, you use the pre-shared secret to make a encryption key, and you use the encryption key. Very simple, yeah, but also not so good, yeah, because the security relies on the third authenticated third party, relies on the PSK security. Meanwhile, we put this in the PUF, yeah, a classical PUF that also speaks PQC, yeah, so we can communicate the PSK from a PUF via PQC into encrypted memory where the computation takes place. So that got better, yeah, but you still are left with the untrusted third party. But not so bad. I mean, this worked for little tiny IoT sensors, yeah, these little chips, yeah, with embedded Python and so on. So yeah, so far that's my vision on how to integrate that. I have 2 more slides. Actually, I've split them up in more, just to give you some more quantum optical stuff, yeah, because we're also doing quantum optical stuff. We're lucky enough that we have a lab now for a year, which we call a quantum lab. When we say quantum lab, this means it's a network, right? I mean, a lab for us is a network, and we are lucky that we have a really, really huge R&D network, yeah, which is completely under our control, and it's called the Germany ring in blue, with a northwest link in red. It's more than 2,000 kilometer fiber link. Currently, it's lit. Yeah, so the amplifiers in there, you can split off certain frequency areas, you know, for experiments. But what we actually want to have is that. Yeah, and we're on our way. Yeah, so it's actually the idea of having a Germany-wide dark fiber, classical lit fiber, and OTT line for optical time transfer, because you need to get the time synchronization right. Yeah. In the middle, that's our Berlin architectural infrastructure. I mean, we have I don't know, several hundred kilometers of dark fiber under our control. They go from Winterfeldstraße, WFD, to all different locations in Berlin, so our own locations, Fraunhofer Institutes, Bundesdruckerei, what have you. And next to that, I mean, we have a satellite network. We don't operate that, but we actually rented a capacity for Iridium and Starlink, and we can use that also as disjoint network path. Yeah, it's very simple, yeah. Because I mean, if it goes on a commercial link up in the sky, I mean, it's very disjoint from a earthbound quantum connection. And we have a room, yeah, which is just a room with rack space and cooling. Yeah. That's now in principle the last slide, but it's split into 6, yeah, just to give you a little bit an idea what we're doing. Yeah. So in 2080, we bought our first QKD system, and we integrated that with a key management system, hardware applications, and all that kind of stuff. Then we were part of the Open QKD project. There we got commercial, productive QKD equipment from Toshiba and ID Quantique. Did the same thing, integrated that, and in that time, we had a use case, yeah, which was actually the integration of PQC and QKD. Nobody wanted to work with us, yeah. So we did it ourselves, yeah, and that's why all the ideas that I showed were actually created and implemented, yeah, in all these times. Today, actually just now, there's a lot going on in our laboratory because we gave our network to QNet. Yeah, QNet is that big German QKD program, yeah, and they have their key experiment 2. I think there are 2 or 3 groups acting now in this lab and using our network to get free space QKD and the QKD network and QKD where they encode more than one information on a qubit, stuff like that. Yeah, so I'm not so heavily involved, but that's going on at the time being. And we're having a big project with Bundesdruckerei. Yeah, they're also interested in QKD, and we're working together. Yeah, and get something up. That's the architecture, by the way, yeah, that we came up with. I mean, we do it in a similar way. You have 3 levels, yeah? Application layer, key management layer, and quantum layer. And in principle, there are QKD systems, there are PQC combinations, there's another QKD technology, and they're all exchanging keys. Yeah, and they do it over different channels, disjoint network paths, yeah? And whatever key they produce, I mean, they put into a key management system, and the key management system gets metadata. Yeah, I'm a QKD key from IDQ at 1330 nanometers. I'm a PQC key with a combination Kyber Falcon, whatever. Yeah, and then the application can decide. Yeah, pulls 2 or 3 keys, or asks the key management to combine them with a key derivation function. That's in principle our integration idea, and that's how our testbed is running. That's maybe the flagship project that's currently going on by my colleagues in Darmstadt. They built a QKD wide area network connection from Bonn to Berlin, 19 hops, I think 700 kilometers. It's going to be ready end of this year. Yeah, I think there's going to be a big publication on that, but it's only for R&D purposes. And as you see, there's also a PQC end-to-end connection included into that. Yeah, that's maybe interesting. We also working with vendors, not just with universities. Yeah, and currently we have QNect in the house. Yeah, QNect is this New York startup. Yeah, I mean they made pretty good PR in the last months. Gotham Q they call themselves, and they invented a entanglement source, a photon source that works on 2 frequencies. It works with 4-wave mixing. Yeah, so 2 pump lasers. Rubidium gas, and then they produce 2 photons, one on 1300, the other one on 700 something nanometers, and they put the 1300 photon on the wire, and we ship this now. We are 30 kilometers, and then we are checking the degree of the entanglement, yeah, between the 2 photons on different frequencies. And we could now recapitulate their result in New York. And since we have a lot more fiber in Berlin, and as they say, better fiber, we want to go further. Yeah, let's see how far we get. Yeah, this is now all in the idea of building quantum internet. Yeah, trying sources. At the end of the day, we want to know how good our fiber is. Yeah, is this ready for quantum? Yes or no? Or do we have to do something special? Yeah, and that's another indication that it seems to work quite well. Entanglement swapping. As I said, we are part of QRX, and we have a project running with the HHI in the context of QRX, where we try to build an entanglement swapping experiment. It works in the lab, and we only have type 2 sources. Yeah, nothing pulsed, nothing clocked. The signal is very, very small. Yeah, but it works. We see it. Yeah, and next step would then be to put this on the fiber. But here we are actually really waiting for the next round of QRX here, where we may get then clock sources. Looking at HUB representatives here, and because they have all this technology ready in principle, yeah, to be tried out in the network. There's one result where we participated also in the context of QRX, and this happened in Frankfurt, in Stuttgart, Peter Michels group. They used quantum dot sources, used a frequency multiplier, sent it over our network, 30 kilometers to a Telecom node and back to the university. And then they did a correlation management between the two, measurement between the two quantum dots. Yeah, worked out quite well. I mean, you see the quotes. And maybe going back a little bit, I think distributing entropy, random numbers, is also worthwhile number beacon. Yeah, maybe a little bit more power, a little bit faster, a little bit more performance under it, because when you distribute entropy, I mean, you can use this for creating encryption keys, forwarding them, maybe build in an easy encryption scheme, but also these wiretap codes. Yeah, they have this common seed. Do you remember? Yeah, we could push it. Yeah, I mean, you could think of pushing enough seed during nighttime in such a mobile cell. Yeah, give it to the handsets during night. Yeah, and then they use that. Yeah, during day when they do traffic and encrypt that. There's post-channel communication. Haven't talked about this today. There's also, I mean, this identification codes. I mean, this, I think we had this in the past days. It's classical, where you get a double exponential increase of channel capacity if the decoder is only accepting yes or no messages or interested in yes or no messages. Very interesting, I think, yeah, because I hear double exponential channel increase, but what you need is common randomness. Yeah, so that's in principle the idea. Yeah. So randomness might get a value in the future networks, yeah? And we're building a service on that. And I think that's it. Thank you.
We have questions from the audience.
We'll leave somebody else talk, but then, so you had these combiners that you were essentially using. What sort of notion of security did you use to show that these keys distributed through different ways were combined securely?
How do we measure that if there's a combined security? I mean, how do we verify that they are combined security? Or
and what scheme did you use? You mentioned that you were using
their standards. Yeah, so they are standards with NIST and even with TS Cyber. Yeah.
Okay.
Yeah, we take one of the implementations and put, yeah, or if you want to be fast for demonstration purposes, it also probably is enough if you do XOR. Yeah.
I mean, generally you would want to use a key derivation function.
Yeah, we're a demonstration engine. Yeah, so that's why. So the proper answer is we use the standardized key derivation functions. Yeah.
And why did you put anti-RU with dilithium? And not Kyber with dilithium.
Yeah, so this was an old slide. Yeah, so in principle, when this all came up and we learned how to use Open Quantum Safe, yeah, the first things we did a comparison of performance. Mm-hmm. Yeah, it's also paper in some NOMS IEEE magazine. You can look it up. What we measured, yeah, we measured the TLS handshake for various combinations and various security levels. Yeah, and Kyber Falcon was actually the optimum. Yeah, and we just picked another combination, yeah, that was available for us. You know? The important thing is you always have to use a different cam and a different SIG, yeah, to hold this argumentation line.
So have you worked with aerial fiber and you know, so you're getting a lot of experience now with running it over different fiber plant, and Are there issues that come up? Do you have patch panels that suddenly give you lots of reflections and problems and these kind of things?
When you have a quantum channel, the first thing you do is you measure the attenuation. Yeah, you have these OTDR devices for that. Yeah, and you see exactly where your splices are, and you want to have as little attenuation as possible. So that's why you start working, yeah, to reduce these bad splices or even connections on patch panels. Yeah, aerial fibers we don't use, we don't have. They're all digged into the ground, at least in our test beds, yeah, and usually in Germany.
Or there's the old story about you got a fiber going across a bridge or something, and so it's
I don't know. So not in our test network, yeah. So no experience, yeah.
Okay.
I heard in Brazil, they have all aerial fibers, yeah. And we once applied for a research project from the EU, or Brazil was also one partner, and there would have been access for a sensing project with aerial fiber, but this didn't work out.
Thank you for your talk. I'm interested in your entanglement swapping device. What are your plans on extending that, kind of using multiple devices in a row, and maybe actually building a quantum network?
Yeah, at the end of the day, that's the goal. Yeah. So, I mean, in this specific experiment, we used time-band encoded qubits, and it was a bicep measurement with a beam splitter. Yeah. And single photon detectors, and a long integration time through a time tagger, yeah, because the coincidence probability with such a type 2 source is very, very low, right? Yes, we want to make that part. The vision is somehow to prototype or the technology that makes a quantum internet, sure, yeah. But at the end of the day, I mean, we come to the end of our financial possibilities, yeah, and these things in a better way will be built anyway in this consortia, yeah, that we are part of, yeah. So, yeah, I mean, we have now photon detectors, fine, yeah. We also have beam splitters, fine. But if you now think about, let's say, quantum storage, yeah, that you want to actually also combine with your bell set measurement, yeah, we cannot build that, yeah. So we cannot. I mean, we don't know how to. But there we rely on our physicists, yeah, that are part of the team. Yeah. But we are good at integrating. Yeah. So that's our role. Yeah. So take the components, try to integrate them, and that's also some point of QKD. Yeah. I mean, QKD normally it's been talked about on the physical layer. Yeah. And then when you're at the endpoint, wherever this is, yeah, it ends. But how do you get the key out of the QKD box? Yeah, how do you manage it in the key management system if your consumer is not, let's say, in the same rack? Yeah? Okay, maybe again PQC, but then you have. But for the hardcore security analysis, if you want to really go for eternal security, I mean that's a showstopper. Yeah, in principle, also the trusted node is a showstopper. Yeah.
Mark, I want to trigger you shortly before we hand over to Bulat. What is your experience with open source? Is the implementations that you did? Of course, when you implement Kyber or something like that, I assume you know what the code is doing. You can inspect it. What about the QKD solutions that you tested?
The QKD solutions, I mean, the QKD systems themselves, yeah, they are sealed. We cannot look into them. Yeah, so we don't even have a root password. The key management we built ourselves, so that we know what we're doing. Yeah, and the application in the easiest way, it's a hardware encryptor. Yeah, like an ATFA box or something. Yeah, which is also sealed, obviously, but this is just an application. Yeah, so you can live with that. Yeah? Or we have our own applications. Yeah. We use open source software. Yeah, we thought about putting the key management open source, but we didn't.
So you have 1, 2, 3, 4, 5.
Yeah, not all of them in there. So we have 12 to 14 nodes.
Are they interconnected or is it a star network?
That's physically a star architecture, logically a fully meshed network.
I see.
A fully meshed quantum network, but we cannot use it, yeah, because QKD systems are not. I mean, the meshing, it works with frequency multiplexing, and normally such a QKD system cannot vary the frequency when you buy it. Yeah, so they're really fixed. That makes it a little bit difficult for us, but in principle, the capabilities are there. Yeah.
Well, I mean, I don't care about QKD. What I care about is what would be the losses on the dark fiber that you have between various endpoints. It would be nice.
They're different. I mean, if you're interested, I can send you a plot, or I look it up, look the values up. Depends on length. I mean, it's the 3 dB on 12 kilometers. Yeah, usually plus minus 2.
It'd be nice to actually have the data, because a lot of these studies, they kind of assume, you know, anywhere from 0.25 GB to 4 GB
Yeah, we did
loss per
OTDR measurements on
kilometer.
all the fibers. Yeah, so we
Yeah.
have the lines where you see the
Awesome.
splices and everything. Yeah.
Is that data public?
No, they're not public. But if you're interested, I mean, yeah.
All
I
right.
mean, the governance of this world network is very simple. Yeah, I mean, it's our network. Yeah, but if you've seen, we did experiments with Stuttgart. Yeah, we did experiments here with the Berlin folks. Yeah, and we're letting QNet in just by call. Yeah, in principle, I wouldn't say it's a public network. Yeah, so but the governance is just ask. Yeah, currently, if we have capacities, we can make a lot possible. Yeah, and in that context, I mean, also the fibers. Yeah, if you do experiments, and you can see the plots. Yeah.
All right.
Just about the distribution of entropy, can you tell me a little bit what is it about? Because entropy is not a physical thing; it's a property.
A random numbers. Random numbers, entropy, high entropy. I always call it entropy distribution. It means random number distribution.
Okay.
It's in a random number beacon. Yeah. What's the idea? NIST has this beacon, yeah, where they put every 15 minutes a random number into the world. Yeah. We can do this as well. Yeah. And
yeah, but the keys are supposed to be random numbers too.
Yeah, sure. Yeah. And then we
so what would be the difference?
Make encryption keys out of that. Yeah. Yeah.
Okay.
So it's an IDQ random number generator, yeah, in appliance. 1 megabit of something of random numbers they pump, yeah, and now it depends how good you want to be. Yeah, you can do your own statistical analysis and see that they are somehow behaving like random numbers before you hand them over to the user, yeah, or you don't, or you believe the vendor. I mean, yeah, but at the end of the day, it's a random number pump, yeah. And the idea for doing that was actually also the collaborations with you, Moritz. Yeah, so WireTap codes. Yeah, they need a lot. They need. You said just 1 bit of seed. Yeah, when you had the question, I thought it would be a little bit more with the realistic channel. So give them room. Yeah, and you're done. Yeah, in a network context. Yeah.
So, Mark, is there any way in which you come up with, say, this epsilon, if you do, say, wiretap coding, or also if you use QKD? Moritz was mentioning earlier today that you have some security metrics, some information theoretic one. You must specify an epsilon of deviation, which you are allowing in your statistics. Have you found some way of coming up with a good number?
This is we are a demonstration engine. For that, I would call Moritz and ask for the epsilon.
And what about the physics?
I'm not a mathematician. I mean, I'm a physicist. Yeah. So, and we have to do cryptography, quantum maths, and all that. Yeah, it's quite a challenge, I have to say. You cannot solve everything. Yeah. So, and I wouldn't also say that I fully understood the QKD proofs. Yeah. So, sorry, but there are people that understand them. Yeah, and that's why we have them. And then I can also believe that. What they find out. Yeah.
Okay, so is do those proofs also come with some, say, do's and don'ts? Like, is secure as long as you don't use it in the wrong way?
Yeah, I mean, there's one fact. Maybe I say that. Yeah, so it took really a long time from BSI and NIST to get the information. Yeah, we asked how long can I use encryption key for AES? 256. Yeah? It really took a long time, but at the end of the day, they sent us some papers where there were some comments, and they said the rule of thumb is 1 terabit. This is our planning number, yeah, where we plan our networks now for. Yeah, so 1 terabit of data, you have to exchange your AES key. If you have a terabit line, yeah, so we have 800 gigabit transponders in our fiber networks. This means every 1.2 seconds we have to exchange the encryption key now on that transponder box. Yeah, that's not possible at the time being. It's an open issue. Yeah, if you have a 100 gigabit line every 10 seconds, might be possible already. Yeah, but not more, I would say. Yeah, but then they say you're fine.
Okay, and regarding the physical layer security mechanisms, we saw some attack on the slides earlier by Nilesh, where people shine light into the QKD system. Would then require to specify?
Yeah, that's why we certify, Janis. I mean, that's the whole role. Yeah, so we create protection profiles. Yeah, where you actually can nail down the security means of such a system, and then it's been you go to the certification lab where the vendor comes, and then you check all that out. Yeah. is the random number generator, does it have vectors? Yes or no? Yeah, do we see any? Does the QKD system stop doing QKD when your attenuator is down also, yeah, in the sender side? I mean, these are a list of parameters, yeah, that are then being checked for after a certification procedure.
It is part of that profile generated by you?
Yeah.
Is that generated partially at least or influenced by T-Labs when we
Yeah,
I mean we are all doing
TSEC
research, right?
So we was part of the OpenQKD project, yeah, where this PP was initially being generated, not standardized, and Nostradamus, as I know, is now actually doing the checks against the PP if the vendors are so reporting. Yeah.
Okay, thanks.
And then we believe, right? I mean, certified, you can use it. Yeah.
But I mean, certification is the result of empirical inquiry into how secure is the system actually and what do you need to make it secure. You can easily have a certified system that's not actually secure. And if you're like, especially when a system like QKD tries to have security properties like everlasting secrecy, for instance, which is this very, very high bar and that's being used for advertisement. If you're relying on certification to achieve that, you might not though.
Yeah, I agree. It's a really hard topic, yeah, but this is normally the way it goes, yeah. So you certify, you can use. If you're not certified, we will never use, yeah, as a telco operator, yeah. That's the first step, having a certified system, and better than a standardized system, yeah, because when you have standardization, then you could have more vendors that are building against common interfaces and that kind of stuff. In side channel analysis, I mean, you never know. Yeah? I mean,
if I may make an analogy here, like that sounds to me like another one of these field transitions where you're like having one field where you're actually like trying to be empirically correct, and then you're doing a transition to the legal field, and now you're working with legal definitions that might be good enough. So that might also be one of these places where it's really important to look to manage this transition, to figure out how much information, how much certainty are you actually losing here.
And so I have to ask the question: have you deployed QKD commercially and have commercial customers for it? And are your customers asking for QKD? Do you know? Can you say?
No, we have not deployed QKD commercially. We have this testbed in Berlin. We have a smaller testbed in Darmstadt, and we have this Bonn-Berlin link soon. Yeah, and so we have equipment. Yeah, we have systems. In principle, yeah, that's it. Yeah, so no commercial system as far as I know. Yeah, at the time being.
And you know, or can you say, are there customers who are asking for it or interested?
Yeah, sure. I mean, in principle, the wires are open. Yeah, so banks, financial sector is active. Yeah, so they're on it. Yeah, on this whole quantum security topic. Yeah, and they're doing trials. Yeah, they're also doing trials with us. Yeah, but it's a difference of doing a trial and deciding for a technology and instead of buying a system, right, in the service. And I mean, network operating center connect, yeah, if they're within the premise of 100 kilometers would also make sense as a use case. Yeah. Yeah. The big customer that's out there is the European Union. Yeah. The potential big customer. Yeah. Because the European Union has strong plans, yeah, to deploy a European QKD architecture, either space-driven or ground-driven. They don't know. I don't know. Don't know if they know, but I don't know. And that's a big program, yeah, that's going on. And there are lots of funds being put into this project. I don't know what comes out, yeah, but there are architectures, there's coordination. So my colleagues in Darmstadt, they're pretty active in that. There's Euro QCI was an architecture project that's done. There are 2 architecture proposals on the table. Petrus is coordination of the national QCI activities, that they somehow do the same way. Nostradamus is this test lab. Yeah, and next step would then be maybe press the button. I don't know. Yeah, and build something bigger. Yeah.